Hello, my name is Imogene Frederick, and this is my presentation on the quantum phenomenon of tunneling. So have you ever heard that if all the particles were to line up perfectly, your hand could pass right through a solid wall? While it's very, very, very unlikely, quantum tunneling phenomenon says that that possibility is not zero. Quantum tunneling on a micro level is what allows radioactive decay to exist and a lot of other thermonuclear reactions. But to really understand it, we first have to delve into wave-particle duality as well as the uncertainty principle associated with it. Wave-particle duality, as the name suggests, is where we can model something as both a particle and a wave. Light is a great example of this. As we're learning in class, we have the double slit experiment, which when we shine light through two slits, we have a clear wave interference pattern as shown in this picture here. And that is hard proof that light acts as a wave. But this conclusion is actually countered by the existence of black body radiation and the photoelectric effect. And these things, we're in a complicated situation with the ultraviolet catastrophe, which we learned about in class, so I'm not going to go over. But in the end, these mysteries were solved by Max Planck's idea of energy quantization, which made us realize that light can be made up of particles called photons. So because light both acts as a wave in the double slit experiment, and in black body radiation and these photoelectric effects, it acts as particles or photons. Duality has to exist because both of these things have been proven to be true. So this wave duality is very important for quantum mechanics, and its understanding has helped us to describe the quantum state of particles through wave functions. And these wave functions describe lots of different qualities of our system, including the momentum, the probability of position, which is most important for quantum tunneling, but it also describes the spin of these particles too. And Heisenberg's uncertainty principle, right here, basically takes the wave function and tells us that because our perception of the quantum realm is so limited, we cannot with certainty know the position and the momentum at the same time. So therefore, we can't pinpoint the exact location of particles. We can only find the probability that they are at a certain position. And this is very important, and you will see why once we get exactly into this phenomenon. So let me set the stage. Here we have a little particle or a ball and a potential barrier, and this could represent the repulsion between like charges or an actual physical wall. In classical mechanics, this ball would either roll over the hill if it has enough energy, or if it doesn't, it would go halfway and then roll back down. But in quantum mechanics, our particle doesn't have enough energy to go over, but it just goes through. It effectively teleports. Because the wave function spans throughout our system and we cannot be certain of its position, there is a sliver of possibility that our particle actually is on the other side of the barrier. And just because it has a possibility doesn't mean it always happens. So not all particles will tunnel, but there are enough particles that enough of them do. This is better shown here in this picture. When we consider the square of the amplitude of a particle, that's the position of it. So in this image, you are seeing the amplitude be pretty high before the barrier. It decays going through the barrier, but there is still a level of amplitude or probability of position that the particle is beyond the barrier. And this decaying through the barrier makes sense because the thicker the barrier, the less likely a particle is to tunnel. A good visual of this idea is shown in this GIF here. As we can see, if the y-axis is considered to be a potential energy barrier, this wave function encounters our barrier, and a portion of it continues beyond the barrier. So there is a probability that our particle continues, even though it has encountered a repulsion force or whatever you have. So quantum tunneling, while it is complex, it is essential to life. It is responsible for nuclear fusion in the sun, without quantum tunneling, the hydrogen atoms wouldn't be able to overcome the repulsion force and bond together to make helium atoms and therefore create life. We wouldn't have radioactive decay. We wouldn't have a lot of nanotechnologies that we have today. So we have to consider quantum tunneling when we're making anything from wires to intricate chips in our computers. Um, One of the coolest things that has come from our studies of quantum tunneling is actually the scanning tunneling microscope. Okay, so this scanning tunneling microscope effectively works to allow us to see individual atoms and examine DNA strands. The way that it works is basically by running a voltage through this metal tip of our scanner and through the sample down here. Then we run this tip very, very close to the surface of the sample, but without touching. So without the quantum model, the electrons shouldn't be able to jump up and complete the circuit, but with tunneling, they can. And this means that small bumps in the sample will either shorten or lengthen the gap to make the current increase or decrease. This change can be measured and recorded by the microscope, which then results in high-resolution images at the atomic scale, which allows us to manipulate or understand materials on a quantum level, which is crazy. This has allowed scientists to examine the lattice structure of materials to more deeply understand their properties, which is extremely helpful for manufacturing. So as for the future of quantum tunneling, while it has already done a lot, it is still continuing to open the door for greater advancements. We're talking advancements like in data transmission. Instead of having to use amplifiers and demodulators, which greatly limit the carrier frequency and possible data transfer, we could instead use tunneling transistors. The idea of these is that they are highly sensitive and can pick up on way lower frequencies, which would allow us to send a lot more data more effectively. And because in our modern world, communication and the transfer of data is very important, this could mean a lot of things for our future. Beyond that, who knows? Maybe quantum tunneling will lead us to a future where teleportation on the macroscopic scale isn't just a sci-fi dream. Here are my sources. And if you're interested on more on the topic, here's a link to a pretty cool simulation that I found, and it was fun to play around with. But other than that, thank you for watching. I appreciate your time, and I hope you learned something.